Hi, everyone. So my name is Kaitlyn, and I'm from Western University in London, Ontario, Canada. And my talk today is about investigating alignment-free machine learning methods for HIV-1 subtype classification. Okay, so to start, human immunodeficiency virus 1, or HIV-1, is a global public health concern and affects over 40 million people worldwide. So HIV is divided into four main groups. So there's group M, group N, group O, and group P. Oh, I guess you can't see my cursor. There we go. So group M, N, O, and P. But for the focus of most of today's talk, we'll be looking at group M. So group M is further divided into over 100 different subtypes. So there's pure subtypes that are denoted with letters A through K, and a number of recombinant subtypes that are denoted, or that are like circulating recombinant forms. So they occur from recombination events between other like pure subtypes and other recombinant forms. And there's a lot, and these HIV is basically divided into these subgroups based on genetic similarity. And there's a high degree of diversity both within and between subtypes. And there's and due to this like genetic diversity, different subtypes have varying degrees of pathogenicity and respond differently to different treatments. So HIV subtype classification is crucial for infection management, and it's relevant for developing new treatment methods as well. So we know that HIV-1 subtype classification is important. So how do we do it? So traditional approaches were alignment-based that involved basically taking an input genome and basically aligning it with reference sequences. And some tools that are BLAST-based would look at identifying homologous features, while others use that sequence alignment to construct maximum likelihood phylogenies. However, these alignment-based approaches are computationally expensive because there can be scalability issues with long sequences, so working with entire genome sequences, as well as large data sets. And also with sequence alignment, there can be some reproducibility issues because it basically relies on having a manually curated reference sequence, which might not necessarily be the case. And it also relies on ad hoc parameter settings for handling gaps and mismatches. So there's different ways that we can penalize like a gap opening. So that can kind of lead to reproducibility challenges. And also alignment is difficult in diverged regions. So to address that, there's been a variety of different alignment-free HIV-1 subtyping methods that have been developed. So the approach is fairly straightforward. So it involves basically representing sequences numerically, so basically creating vectorizations or embedding sequences, and then using machine learning methods to classify sequences into subtypes. So as we see in this table, so there's been a variety of different vectorization methods. Some are K-mer-based, while others use a natural vector method, which we will get into in a little bit. And some incorporate positional information as well. And we see that there's a variety of different machine learning methods. So we have our support vector machines. We also have linear discriminant analysis, as well as k-nearest neighbors approaches. And these methods have high accuracy. However, for the less common subtypes, some methods have poor recall, and some achieve like 0%, so they misclassify all of the rare sequences. And also some of them were developed for only one gene. So there's some areas for improvement. So our work is really motivated by, we really want to compare sequence vectorization methods, because in machine learning, the format of your data is just as important as the choice of your model. So there's been limited work comparing the different vectorization methods across machine learning models. And a lot of these approaches use kind of similar ideas with K-mers, nucleotide distribution, and average position of nucleotides within the sequence. So our work is motivated by two main questions. So we want to know, how does the sequence vectorization method affect HIV-1 subtype classification? And we want to know if we can use natural language inspired vectorization methods for HIV-1 subtype classification. So basically, with our ultimate objective is, can we find a better model to classify HIV-1 subtypes? So for an overview of our work, so we start with, oh, I guess we can't see. Okay, so I'll direct your attention to the yellow panel. So we have basically our sequences, and we use 10 different vectorization methods. So we use k-mer-based, natural vector-based, as well as natural language processing. Thank you. Okay, thank you. Okay, so I have my laser pointer. Yay. Okay, so we have our sequences, and we apply 10 different embedding methods. And then because we're working with whole genome sequences, our data is really high dimensional. So we want to see if we can and should reduce the dimensionality of the data and to see whether that affects our performance. So for dimensionality reduction, we apply PCA. So then we have our feature vectors. So then we take our feature vectors and our labels, so which are the HIV subtypes, and then we apply 7 different machine learning methods. So we have support vector machines, logistic regression, XGBoost, lasso, k-nearest neighbors, naive Bayes, and a one-dimensional convolutional neural network. And then we evaluate it across a variety of different metrics. So for our data set, so our data set comes from the Los Alamos National Laboratory data bank. So we downloaded all of the HIV full-length HIV-1 sequences from the Los Alamos database. So there are about 20,000 or so. We apply some filtering to reduce sequences that have unknown, like basically unknown subtypes. And we also reduce sequences that have fewer than like 19 examples, because this number of 19 examples has been established in the literature as a kind of reference point. So overall, we have about 15,000 different sequences, and the average length is about 9,000 nucleotides. And these represent 18 different subtypes, ranging from 19 samples to 9,806 samples. And they account for 19 recombinant forms and 9 pure subtypes. And because we see from this very large number, our data set is clearly imbalanced. So this is because one of the subtypes, subtype B, which is prevalent in North America, accounts for like the majority of the sequences in that database. However, this proportion doesn't necessarily reflect HIV subtype distribution worldwide, because subtypes A, C, and the recombinant form that's CRF01AE are the most prevalent worldwide. However, because this database is collected based on sequences in North America, it's heavily biased towards subtypes that are the most common in North America. And so to address this imbalance, we apply some oversampling. So we explore a variety of different methods. So we first tried a conservative approach that's just tripling the number of sequences in the minority classes. And we also tried synthetic minority oversampling, and we actually found that our naive method seemed to work the best in our cross-validation studies. And also in our data cleaning, and so because we exclude samples of unknown origin, all of our data is labeled. So now we have our data. So now it's time to explore the sequence vectorization methods. So the first method that we use is ordinal encoding. So this is a very naive baseline that basically represents each nucleotide as a number. So in this example here, A is like a number between 0 and 1. And so typically for categorical data, the choice of one-hot encoding might be more appropriate. However, for the machine learning methods that we are using, the extra channel dimension that one-hot encoding introduces doesn't work with some of the R classification models. We use the scikit-learn library. So that's our ordinal encoding. It's basically our naive baseline. So next we use k-mer frequency. So k-mers are basically substrings of length k, and we basically count the frequency of all of these substrings within the sequence. So the values of k that we explore are 5, 6, 7, and 8, and these values are k-mer values that are typically used in like the literature for HIV subtype classification. And so for k-mers, there are 4 to the k possible k-mers. So for example, for if k equals 2, there's like 10 different or 8 different ways to basically count k-mers. So we basically, our k-mer method is just the frequency of each of the possible k-mers. So then we explore the natural vector encoding. So the natural vector is basically a 12-dimensional encoding that incorporates the nucleotide frequency for each nucleotide, as well as its average position, and as well as the variance. So it's a very high-level, simple encoding for nucleotide frequency. And there's also an extension of that that was developed that includes covariance. So natural vector with covariance basically just introduces additional features representing the pairwise covariance between all the possible pairs of nucleotides. So this, compared to the k-mer encoding, our natural vector encoding has like lower dimensionality. And there's also the most recent natural vector encoding method is subsequence natural vector encoding, which basically involves dividing the sequences into subsequences and then computing the natural vector for each subset. So this kind of gives a sense of like local nucleotide distribution. So it adds a little bit more dimensionality as well. So maybe there's a little bit more data in that encoding. And then in terms of our natural language processing encodings, we look at word2vec, which is an NLP technique that's used for generating word embeddings. And word2vec basically works by capturing semantic relationships between words based on their co-occurrence patterns. But since we're working with sequences, we don't really have established words. So for our study, we consider k-mers as words. And we consider k-mers of length 5, 6, 7, and 8, as we do in our k-mer encoding. So basically, word2vec learns embeddings by predicting target words based on context words. So for example, in the sentence, the cat sat on the mat, some target words could be the cat sat on the, the context words would be the cat sat on the, where the target word would be mat. So it's basically using semantics or like the context to predict the target word. So we're basically leveraging that idea using k-mers. And so basically the word2vec model is like predicting the target words. And to do that, it's iteratively refining this embedding matrix. So what we do is we basically extract this embedding matrix, which is the word2vec's internal representation of the k-mers, and we use that as our feature vector. And then we also consider TF-IDF, which is term frequency inverse document frequency. And it basically measures the importance of words in a document relative to a corpus or like a collection of documents. So our intuition is basically by weighting our word2vec embeddings, we could capture maybe some relationships along with the significance of k-mers, which maybe could help with classification. So those are, as a quick overview of our 10 different encoding methods. So now for our machine learning methods. So we use 7 different methods. So we explore logistic regression, which is basically, so all of our machine learning methods we consider basically a one versus rest for our traditional approaches. So for logistic regression, it's a basically probability-based binary outcome prediction. So we basically classify one versus all of the other subtypes. Then for lasso, it's essentially sparse coefficient linear regression. And again, we do one versus rest, where support vector machines basically work on maximizing the kind of distance between two, like the margins. So if we consider the triangles are one group and the circles are another group, the solid lines here represent the margins in like the margins, and the dotted line represents the hyperplane. So a support vector machine basically tries to maximize the distance between like the margins essentially. And then we have XGBoost, which is a gradient optimized decision tree ensemble learning method that basically iteratively refines the like predictions. And then we have our k-nearest neighbors, which classifies, so our k-nearest neighbors implementation, we implement the majority vote and we explore both the Manhattan distance and Euclidean distance, but we find that the Euclidean distance seems to perform better than their models. And lastly, or we also look at naive Bayes, which is our last kind of traditional machine learning model. So it's probabilistic, and it basically assumes that there's independence between each of the features, and it's also based on a Gaussian approach. And we also explore convolutional neural networks. So we use one-dimensional convolutional networks for our like sequence data. And convolutional neural networks are basically hierarchical models that are really good at learning features in data that has kind of spatial relationships. So they could work well for sequence classification or subtype classification. And we just an overview of our evaluation metrics. So we consider accuracy, which is the percentage of classified subtypes, just in general, not looking at specific classes. So when you have imbalanced data, this can actually really skew the accuracy. So it's important to look at kind of per class accuracy. So we look at balanced accuracy, which is also the same as macro recall. And it's basically the percentage of correctly classified subtypes, but all of the categories are weighted equally. And precision is basically the model's ability to classify all of the all instances of a subtype, where F1 score is the harmonic mean of precision and recall. So it gives a good overview of the model's performance in general. We also have OROC and AUPRC, which are the area under the receiver operator characteristic and area under the precision recall curve. And finally, we look at Cohen's kappa, which measures the agreement between two basically like predictions, and it corrects for chance. So now for our results. So ordinal encoding is, if we recall, is our baseline encoding. It's the really naive approach that just uses, that just encodes each nucleotide as a number between 0 and 1. And as we can see, it has fairly high fairly high accuracy for lasso and SVM. However, that cannot tell the whole story because our data set is so severely imbalanced. We need to rely on other metrics. So we can see from our balanced accuracy, precision, and all the rest of the metrics basically, that our model does not perform well for minority classes, and it basically tends to just predict the dominant class, which means it's not really learning anything from this one. So now we look at our our like natural vector-based methods. So we explore, so if we recall, we have their natural vector method, we have natural vector with covariance, and subsequence natural vector. And we find overall that as we basically increase dimensionality in our natural vector methods, the models perform better. So subsequence natural vector, because it's higher dimensional, there's probably more patterns for it to learn, is our best performing natural vector method. So we see there's an improvement in accuracy. And again, we see that lasso and logistic regression. are performing well. We see our balanced accuracy is not that great at about 60%. Our precision is decent, but overall, it's better than ordinal encoding, but we can probably do a little bit better. So now we look at our word-to-vec encodings. So we find actually that word-to-vec outperforms TF-IDF-weighted word-to-vec, and which achieves a balanced accuracy of only 0.32, where our word-to-vec model achieves a balanced accuracy of 80% with logistic regression, as well as the sport vector machines. So this could possibly be due to the fact that there's so much variability between HIV subtypes. So this kind of could, it might not be the best indication of kind of defining features for HIV subtypes. But for word-to-vec, we find it has very good accuracy at 98%. But again, there's a caveat that our data is imbalanced. But then we see overall precision and F1 score, OROC, and AUPRC are decent. So it shows that it definitely has better performance on predicting majority and minority classes. But despite word-to-vec's promise, we do find that the kind of traditional k-mer-based encoding is our best performing method. So we look at our 4 different values of k-mers. We find that as we increase k from 5 to 6 to 7, the performance increases. However, we find that that actually doesn't hold true going from 7 mers to 8 mers. But if we recall that when we do k-mer encoding, there's 4 to the k possible encodings. So for an 8-mer, 4 to the power of 8 is in around like 60,000 to 70,000, which is very high dimensional. So that is a very, very sparse vector. So we think that because it's such a sparse encoding, it probably is introducing a lot of noise that's making it difficult for the model to pick up on the signal. So we find that overall, the 7-mer encoding is the best for k-mers, and it's actually the best overall of the models that we explored. So we see that XGBoost across the board outperforms like the other machine learning models. So it achieves accuracy of 98%, which is a little bit higher than what we see in the literature. We have a balanced accuracy that's pretty good at 84%. Our precision is high. Our F1 score is 87, which again gives a good indication of model performance. And we also have like good values for OROC and AUPRC. So it basically shows that it's performing well on majority and minority classes. But from these metrics, we see there's still some room for improvement, because it would be nice if the AUPRC value were higher. So then for a closer look, we have this confusion matrix. So it might be a little bit difficult to see. So this confusion matrix is basically normalized by the counts for each classes. And I just want to draw your attention to this darker green line. So this basically, if we were to see a dark green line going diagonally, it would basically represent perfect classification. Oh, here we go. Okay. So we see that overall, the model is doing pretty well. However, there are some mistakes that it's making. And then we look at what types of mistakes is it making. So we basically look at pure subtype A3 here, and we see that it's like performance is not very good. And when we actually look at our data, subtype A3 has the fewest number of examples. So there's only 19 examples. So that kind of makes sense for why the model might be making some mistakes when it's classifying that. We also find that it tends to make mistakes for classifying. It kind of tends to confuse our like CRFs, which are our circulating recombinant forms. So we see, for example, CRF7 and CRF31BC. So these recombinant forms are derived from unique recombination events between subtype B and subtype C. So they're basically, these recombinants are composed of the same subtypes, but they're just kind of shuffled in different ways. So that kind of makes a little bit of sense for why the model might be missing that. So it's kind of correctly identifying that it's likely subtype B or subtype C related, but there's still a little bit of room for improvement in that sense. So overall, we find that our k-mer encoding outperforms all of the other metrics that we explored across all metrics and also for all of the machine learning models. And in particular, we find 7-mers with XGBoost works particularly well, which this result isn't necessarily surprising because XGBoost tends to perform really well for a lot of sequence classification type problems, and k-mer is a fairly standard approach. And we also find that XGBoost, lasso, and logistic regression also perform well against like across various sequence vectorization methods. And this is kind of almost an indication that it's always good to start with the simplest models, like to start at the basics of the simplest models before kind of throwing deep learning at a problem. And we also find that although word2vec doesn't outperform k-mer, there is kind of a lot of promise because it does still achieve our second highest balance accuracy. And some of this performance might be hampered by the fact that word2vec was specifically designed for natural languages. And although it might not be able to fully capture kind of local sequence structures, it does a pretty good job, but it's not really fine-tuned for this approach. And its performance might suffer basically because it relies on semantic relationships that are more designed for natural languages. And also, we also think there's room to explore a variety of more sophisticated oversampling methods to really address that class imbalance. So overall, HIV-1 subtype classification is crucial for patient care and the development of new drugs and vaccines. Although sequence alignment-based methods can be easy and useful to use, they can sometimes be infeasible for large data sets. And as far as alignment-free HIV-1 subtype classification goes, we think it's just as important to consider the machine learning model as the representation form as your data. And also we think that there could be some future work investigating convolutional neural networks and other deep learning architectures. And my references, and I'd like to acknowledge my supervisor, Dr. Pingxiao Hu, and the rest of my lab mates. And I'm also would like to acknowledge my funding and sources of support. And I would be happy to take any questions.
Okay, I think we have time for just one question while Alexandra can come up and set up. Any questions? I should have said as well, this was one of our proceedings talks, so this paper is under consideration at Bioinformatics Advances. I guess I have a question for you. Yeah. So have you delved into what the features are that are driving performance of the different methods?
That is next. What we're thinking of doing is the idea of interpretability and explainability.
Okay.
Good. Thank you. And I forgot to mention that our code is available on GitHub. I'm sorry I did not include the link.